Welcome to chapter 10 in Math 121. We're going to explore the third section here, which is polygons, perimeters, and tessellations. Tessellations are a lot of fun. All right, let's jump in. So objectives, name certain polygons according to the number of sides, recognize characteristics of certain quadrilaterals. Quad here should be familiar. That means 4. If you've ever ridden on or driven like a quad, we live on farm country here, so in this area, so quads are unfamiliar to many people, and that's a short for the number of wheels. But quadrilaterals have 4 sides, so that should be something familiar. Solve problems involving a polygon's perimeter, and then find the sum of the measures of the polygon's angles, and understand tessellations and their angle requirements. All right, let's dive in. Polygons and perimeters. So a polygon is any closed planar shape formed by 3 or more line segments that intersect only at their endpoints. So this is not a polygon, even though it's 3 sides and it is enclosed because I've extended beyond here. That's not a polygon. Whereas if I were to draw that, that's a triangle, which is a polygon. This is it has 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 sides. Okay, so it's a 5-sided polygon. Pretending to draw straight lines. This is not a. Oh, it's. I'm trying to draw a circle here. Those look like glasses. So circles are not polygons because they don't have edges. Edges are straight line segments. So line segments are called edges, and edges. So they don't have edges, then it can't be a polygon. So a regular polygon is where all of the sides are the same length and all the angles have the same measure. So back here in chapter 2, we saw a regular polygon. The regular triangle was here. So we call that an equilateral. Equa meaning like equal, right? The same length or same side. And here the angles and the length of the sides are the same. So that's an example of an equilateral, or sorry, of a regular polygon. A square is another example. That's not a square. That's pretty good. Hey, that's pretty good. So here, all the angles are 90 degrees and all the sides are the same length. So a square is a regular polygon. Perimeters of a polygon are found by adding up the lengths of the outsides, right? So if it's a square and it's a length 2, okay, then think of if you started here and you walked this way, you'd walk 2 units. Then you walk this way, you walk 2 more units. And you walk this way, you walk 2 units, and then you walk back up. Okay, so starting here and walking all the way around, how far did you walk? Well, you walked 2 plus 2 plus 2 plus 2, so a total of 8. Okay, if I extend this down and pretend that this is a rectangle, it's a polygon, but it's not a regular polygon. This could be like 2, and this could be like 3, for example. Then the distance you start here, you walk this way, that's 2, plus 3 more, 5, plus 2 more, that's 7, plus 3 more, that's 10. Okay, so that perimeter in that case would be 10, whereas this one would be 8. Okay, some common regular polygon names. You have the triangle with 3 sides, that's the equilateral. You have the quadrilateral, that's equal, that's the square. Regular pentagon, regular hexagon, regular heptagon, and then the regular octagon. So think of, you might see these often in your neighborhood. It has the word stop written on it. So every stop sign is an octagon. It's actually a regular octagon. Okay. Parallelograms are a special type of quadrilateral where you can see that the opposite sides are congruent, meaning they're the same length. And then opposite angles are congruent as well. So this angle is congruent to this angle, this angle is congruent to this angle. The perimeter you can find by adding up the lengths, and then the area is the space times the height, though a rectangle that's been kind of pushed over is a good example of a parallelogram. Yeah, rhombus is very similar to a square, but the difference being is that it doesn't have all right angles. Okay, so a rhombus is a generalization of a square in this regard. A square that's been kind of moved, that's a rhombus. And a rhombus that has right angles is a square. So a square is both a rhombus and what am I trying to say? A rhombus is a parallelogram. A square has got parallel sides. A square is a special case of a rhombus, and a rhombus is and a square is also a special case of a rectangle. So squares have a lot of categories that it falls into. So parallelogram with right angles is a rectangle, and then a square, of course, is the special case we already mentioned, and then a quadrilateral with exactly one pair of parallel sides is called a trapezoid. So notice the top and the bottom are parallel, but the sides here are not parallel. So that's a trapezoid. This geometry happens a lot in construction. All right, example one, in a application of a perimeter. Okay, so fencing costs are $5.25 per foot. Find the length to enclose, or find the cost to enclose the following fence. So if we're building around a yard, for example, that's usually a rectangle. And so since the cost per foot is the length along the outside, then we need to figure out what's the perimeter here to multiply it by the 525 to know how much it's going to cost us. So again, this formula isn't coming out of nowhere. It's if I call this L and this W, then if I start walking here, it's walking this distance, so that's 1L. Walking this distance, that's 1W. And then so I'm adding L plus W, and then I'm going to add another L, walking back up here, and I'm going to add another W. So the perimeter here is L plus W plus L plus W. And then if you count, how many W's do you have? I have 1 and 2. And how many L's do you have? I have 1 and 2. So I have 2L plus 2W, which gives us then the relationship for the perimeter of a quadrilateral. And so just plugging in the numbers, if you know the distance, so somehow it's given us the distance there, though I don't see where these numbers are coming from. It says it's 42 yards along one and 28 along the other. And so 48 and 22 looks like it might have been written there. But anyway, we get that the total distance is 140 yards. So multiplying the 140 times the 525 then would give us the cost of the fence. So that's $2,200 and $2,205. All right. The sum of the measures of the polygon. Okay, so this relationship won't go into where it comes from, but it's not too hard to think about where it might come from. And so the sum of the interior angles is n minus 2 times 180. So let's look at triangles. We proved that this was 180 degrees. So there are 3 sides. So 3 minus 2 is 1. 1 times 180 gives us indeed. So it works for that one. Yeah. And then a square or rectangle, it has 4 sides. And I claim that it's 360 degrees inside the interior angles there. Okay, so 4 minus 2 is 2. 2 times 180 is 360. So that works out as well. All right. Tilings and tessellations. A pattern consisting of the repeated use of the same geometric figures to completely cover a plane, leaving no gaps and no overlaps. That's what a tessellation is. The sum of the measures of the angles that come together at each vertex is always 360 degrees. I think that if you just kind of zoom in on any particular point, right? So if you have a pattern and then you have another pattern coming in like so, and then something else like so, the angles at which they meet, if you go around it, always has to equal 360 degrees because you're kind of like zooming in a circle, right? So it's always got to equal that same value. So those exterior angles always have to equal. Otherwise, they don't fit together. And so here's some tessellation patterns, right? You have these, what is this? 1, 2, 3, 4, 5, 6, 7, 8. So these are octagons and squares. Yeah. So in order to tessellate this entire plane, we need each of these angles to be exactly totaling 180 degrees. So if you have 90 degrees up this way, right? That means the outside measure is 270. So that means that these 3 angles here have to be 270. All right. Angle requirements and tessellations. Explain why a tessellation cannot be created using only regular pentagons. Well, regular pentagons have a total of 108 degrees. And so on the interior, not a total, I'm sorry, their measure is 108 degrees for any one of the rectangular angles here, right? Which we've found by the n minus 2 divided times 180. Okay, and then you divide by 5 because that's what each of the interior angles are. So that gives us that these are 108, 108, 108. So those don't add up to 360. There's this weird gap that is too small to fit another pentagon in there. And so you can't tessel with only oh yeah, so that's what we're doing here. So you can't tessellate with only pentagons. So it kind of gives you some really cool observations about how things fit together in a plane, and that's really good for if you're doing any kind of tiling, for example, on your in your kitchen or whatever like that. This is exactly what they do in creating those connections and those patterns. All right, I hope that was helpful, and I will see you in the next video.